Presenting Relational vs. NoSQL Databases by Stephanie Smolewski. What makes a database right for you? Overall, a database is an organized collection of data. There are four main types of databases: a text database, desktop database programs, relational databases, and NoSQL databases. A text database is as simple as it sounds, just some data organized in rows where each row in the file represents a record. You can update records, remove rows, add rows, all of the most basic functions you could perform as if you created this database by hand on paper. A desktop database program is something we are all intimately familiar with. Take Microsoft Excel. These programs allow users to enter data, store it, protect it, and retrieve it when needed. The benefit of desktop database programs over text databases is the speed of changing data and the ability to store large amounts of data while keeping performance of the system manageable. As we become more focused on our system performance and speed, we now head into the worlds of relational databases and NoSQL databases. The relational database model is more practical for business use than the previously discussed text database, since they allow multiple users to not only have access and work with this data at the same time, but also provide a heightened security to protect the data as well. This takes us to our more innovative type of database, the NoSQL and object-oriented database. The difference between the RDBMS approach and the NoSQL approach can be broadly explained with one concept: horizontal expansion. With the traditional RDBMS, we are constantly expanding vertically with rows upon rows upon rows. Throughout the duration of this project, we will be focusing on the comparison between relational databases and NoSQL databases. Specifically, I hope to demonstrate the following points. What is a relational database and who benefits from the use of them? What is a NoSQL database and who benefits from the use of them? We will compare the powers and limits of the two with a deep dive into the DynamoDB, which is Amazon's NoSQL database system, and Microsoft's Azure, a general-purpose relational database. We will explore the possibilities that could lead to one database performing better than the other, depending on the type of data, whether it's transactional or archived, or situations where a crash could occur, and anything else that affects the comparisons of these databases. What is a relational database? The concept of the relational database was born in 1970. A relational database is comparable to a spreadsheet where we can think of the overall workbook as a database containing rows and fields, or columns, with the individual sheets as tables. With a relational database, you can quickly compare information because of the arrangement of data in columns. The relational database model takes advantage of this uniformity to build completely new tables out of required information from existing tables. In other words, it uses the relationship of similar data to increase the speed and versatility of the database. The relational part of the name comes into play because of the mathematical relations. A typical relational database has anywhere from 10 to more than 1,000 tables. Each table contains a column or columns that other tables can index to gather information from that table. Now take a look at the UML diagram to the left. Each table name can be found at the top, highlighted in gray, with each field name listed below. This is a great visual to demonstrate how easy it would be to write a query pulling information from this database. Notice in this particular UML diagram, the table order item 2NF has a one-to-many relationship with the order 2NF table. This means that each order from the order 2NF table can have multiple order items 2NFs assigned to it. Let's take a look at a quick relational database example. Here we have the employees table, and here we have the locations table. Notice in the employees table, the primary key is the employee ID, where each one is a distinct number and letter or alphanumeric combination. In the locations table, we can see that the primary key is the building ID, but this is a more special primary key since this primary key is created from the building name appended with the zip code. Now, What are the main properties of a relational database? Typically, when designing our database, our goal is to maintain consistency in case of a failed transaction. If your application is going to focus on doing many database transactions, it's important that those transactions are processed reliably. This is where ACID comes in. This is the set of properties that guarantee a database transactions are processed reliably. Atomicity, consistency, isolation, and durability. A transaction is simply a single logical unit of work which accesses and possibly modifies the contents of a database. The most simple examples we can think of when trying to decipher what exactly is a transaction can be seen in our everyday life, something like a transfer of funds from one bank account to another, even involving multiple changes such as debiting one account and crediting another, is a single transaction. As mentioned before, the goal of consistency just ensures that the state of the database will not be altered if any part of a transaction before or after fails. Now let's define our ACID properties. Atomicity. A database follows the all or nothing rule, or the database considers all transaction operations as one whole unit or atom. Thus, when a database processes a transaction, it is either fully completed or not executed at all. Consistency. This ensures that only valid data following all rules and constraints is written in the database. When a transaction results in invalid data, the database reverts to its previous state, which abides by all customary rules and constraints. Isolation ensures that transactions are securely and independently processed at the same time without interference, but it does not ensure the order of the transactions. For example, the problem from lecture. User A withdraws $100 and user B withdraws $250 from user Z's account, which has a balance of $1,000. Since both A and B draw from Z's account, one of the users is required to wait until the other user transaction is completed, avoiding inconsistent data. If B is required to wait, then B must wait until A's transaction is completed and Z's account balance changes to $900. Now, B can withdraw $250 from this $900 balance. Durability. In the above example, user B may withdraw $100 only after user A's transaction is completed and is updated in the database. If the system fails before A's transaction is logged in the database, A cannot withdraw any money and Z's account returns to its previous consistent state. It is extremely important to note that an RDBMS instance sitting within one physical server can cause several issues when we turn off the traffic. This is why scalability is important once our server begins to see an amount of traffic that it cannot handle. But isn't there still a potential issue here? Yes, because any physical server can fail no matter how much we scale up. Once we start experiencing these issues, it's most likely time to move to a NoSQL database solution. Overall, relational databases have been proven to be useful through years of tried and true data exchanges. They are well established, we can gain standard data access through SQL, and there is a fixed schema. So why do these sometimes fail where a NoSQL wouldn't? They do not handle unstructured data well. It is tough to manage the indexes, and they are not very good at storing very large amount of data. They struggle to scale easily in certain scenarios, which stems from the fixed schema. The type of person or company who would benefit from a relational database model is somebody who is handling a lot of complicated querying, database transactions, and routine analysis of data. Next stop, what is a NoSQL database? As you can see from above, the RDBMS model truly is great until you reach a point where you now need to store large volumes of data. Cue the NoSQL databases. NoSQL DBs do not require the following: specified data types or set schema or structure. A NoSQL is an approach to databases that represents a shift away from the traditional relational database management systems. Relational databases rely on tables, columns, rows, or schemas to organize and retrieve data. In contrast, NoSQL databases do not rely on these structures and use more flexible data models. NoSQL can mean not SQL or not only SQL. As RDBMS have increasingly failed to meet the performance, scalability, and flexibility needs that next-generation data-intensive applications require, NoSQL databases have been adopted by mainstream enterprises. NoSQL is particularly useful for storing unstructured data, which is growing far more rapidly than structured data and does not fit the relational schemas of RDBMS. Common types of unstructured data include user and session data, chat, messaging, and log data, time series data such as IoT, and device data, and large objects such as videos and images. Several different varieties of NoSQL databases have been created to support specific needs and use cases. These fall into four main categories: key value, document-based, column-based, and graph-based. A key value NoSQL database emphasizes simplicity and are very useful in accelerating an application to support high-speed read and write processing of non-transactional data. Stored values can be any type of binary object, whether that be text, video, JSON document, etc., and are accessed via a key. The application has complete control over what is stored in the value, making this the most flexible NoSQL model. Data is partitioned and replicated across a cluster to get scalability and availability. For this reason, key values stored often do not support transactions. However, they are highly effective at scaling applications that deal with high-velocity, non-transactional data. A document databases typically store self-describing JSON, XML, and BSON documents. They are similar to key value stores, but in this case, a value is a single document that stores all data related to a specific key. Popular fields in the document can be indexed to provide fast retrieval without knowing the key. Each document can have the same or a different structure. Column-based. Column-based NoSQL databases store data in tables with rows and columns similar to RDBMS, but names and formats of columns can vary from row to row across the table. Column-based DB groups columns of related data together. A query can retrieve related data in a single operation because only the columns associated with the query are retrieved. In an RDBMS, the data would be in different rows stored in different places on disk, requiring multiple disk operations for retrieval. A graph-based database uses graph structures to store, map, and query relationships. They provide index-free adjacency so that adjacent elements are linked together without using an index. Most NoSQL systems offer horizontal scalability and higher availability than relational databases by sacrificing querying capabilities and consistency guarantees. Horizontal scaling means that the same ACID properties would have to be guaranteed when potentially many servers are involved in one transaction. However, we cannot prevent a server from dying or separating due to network connectivity issues, leading us to create network partitions. A traditional ACID system can't operate in the same ACID mode under these conditions anymore, but a NoSQL system can under the CAP properties. We have consistency, which reads and writes are always executed atomically and are strictly consistent or linearizable. Put differently, all clients have the same view of the data at all times. Availability. Every non-failing node in the system can always accept read and write requests by clients and will eventually return with the correct response, and not with an error message. Partition tolerance. The system upholds the previously displayed consistency guarantees and availability in the presence of message loss between the nodes or partial system failure. Unfortunately, no single system can have all the CAP properties by the CAP theorem. According to the CAP theorem, a sequentially consistent read and write register that eventually responds to every request cannot be realized in an asynchronous system that is prone to network partitions. In other words, it can guarantee, at most, 2 of the 3 CAP properties at the same time. However, the CAP theorem does not state anything on a normal operation. It merely tells us whether a system favors availability or consistency in the face of a network partition. A comparison of DynamoDB, a NoSQL database system, and Microsoft Azure SQL, an RDBMS. Why do we need to choose between the two in the first place? The choice between a NoSQL or relational database system completely depends on what your ultimate goal is, and especially what type of expansion you plan on doing in the future. The true answer is that you don't need to choose between the two, and you can always add and create an additional database to hold whatever data you want and have it behave in a certain way depending if it's a NoSQL or an RDBMS. The main reason I wanted to investigate the difference is to figure out what the correct database system would be for my current and future dev team projects that my team and I are building at work right now. So how are we going to demonstrate a comparison of DynamoDB and Azure SQL databases? First, just to demonstrate some class-learned technical knowledge, I will host a web page via an EC2 instance that will act as our, quote, project management system page. I will then describe different data scenarios and describe the way each type of database system would react and handle high traffic stress in each scenario. So the first thing we did is we launched an EC2 instance. So I have my two running instances right here. Okay. Awesome. And all we did, step by step, we made our new key, our final project.pem. We SSH'd into our new EC2 instance that we just created in AWS. All I did was just run some updates. Okay. And then from here on, we activated our web server. Here we started our web service. Here we just made sure that it would configure in case anything shut off. Okay. And then we created our index.html. So this is just me going back and forth and editing this over and over again. And here we have it. Put this down so we could see